Hello, everyone. We're going to be doing some R code that corresponds with what we've been learning in Chapter 2, Section 2.4. So we've been learning about the binomial distribution and creating confidence intervals. And what I wanted to do is show you how you would do this by hand and then how you could use some shortcuts in R. So let's use an example where we observed 23 successes out of 25 trials. We could then calculate our sample proportion P of successes, and we could get our sample proportion of failures. And we could have some known idea of what we think the proportion of successes are in the population of 0.75, and then our probability of failure would be 0.25. So if we wanted to do a hypothesis test by hand, we could set all of our values, and if we just did a double check, we could make sure, yes, X is 23 or N is 25. And then we could set up the hypothesis test by getting the test statistic. And based on what we saw in the previous notes, we can calculate this by hand by doing the absolute value of the observed probability of success minus the assumed probability. And then we have the continuity correction and then the square root of PQ over N. So if I do that, then I can get my test statistic, which is 1.73. And then if I want to get the p-value, that is the probability of observing a test statistic as extreme or more extreme than the one in my sample, assuming the null hypothesis is true. So in this case, I'm doing a greater than test if I'm doing a one-tailed test. And so I can use this function p-norm. And p-norm says, if you give me a standardized z-score, what is the area associated with that z-score? You can use tables in the back of the book, but I find that it's just so much easier to use the built-in functions in R. So our p-value here is 0.0416, okay? If we were doing a two-sided test and our alpha level was still 0.05, and we could then do alpha over 2 to find the area in the upper tail, we could get the z-score here. And the z-score associated that would be 1.96. And if you notice, this is Q norm instead of P norm. So what's the difference between Q norm and P norm? Well, Q norm says, if you give me the area under the curve, please tell me the z-score. So I gave it the area in the upper tail of alpha 2. Okay, that's alpha divided by 2, 0.05 divided by 2. Lower tail equals false. I was telling it, give me the z-score where you give me the top 2.5th percentile, the z-score associated with the top 0.025 area. That will give me the positive z-score. If I wanted the negative z-score, I could have said lower tail equals true, and it would give me negative 1.96. In our book and in a basic stats class, you may remember that you could take your sample proportion minus z alpha over 2 times the square root of PQ over N. And then you could also do the sample proportion plus your critical value times the square root of PQ over N. So from a basic stats standpoint, I could get the confidence interval for our true proportion. So we'd say we're 95% confident that our true proportion lies between 0.81 and 1.02. Now that's a little strange because, as we all know, the proportion should lie between 0 and 1, but yet our confidence interval gave us a value bigger than 1. We don't super like that. So there's two things that we could do, which is we could do the normal approximation with the continuity correction, okay? And when we do that, we're just subtracting that 1 over 2n and adding the 1 over 2n to the equation, and we still get values that are above 1. And this is really because we're really close to the boundaries. But if you remember in 2.4, there was a large sample approximation with a continuity correction that had the exact lower and upper bounds. And this forces the answers between 0 and 1. And using those formulas, I've coded that here, and I'm going to share this code with you, but you can double check my work that I got the formula correct. I can get PL and PU. And now I finally have a confidence interval that, as it should, lies between 0 and 1, and it's forced to lie between 0 and 1. Okay, so I get a value of 0.7249, 6 and 0.98602. All right, so there are, of course, easier ways to do this besides hard coding in the formulas that you saw in 2.17, 2.18, and 2.19, which is using a shortcut because someone has built this into R. So I'm going to use the formula, the function, excuse me, prop.test. Okay, and I'm also going to use the function binom.test, and we're going to see how those play out comparatively to what we just coded. So if we do prop.test, right, that is giving us the 23 out of 25. We're comparing that to the probability of 0.75. We get our p-value of 0.0834. And that's very similar to what we got earlier. We did a one-tailed test earlier, but we could have found the two-sided p-value if we wanted. And then we could do the binom.test. And we have a two-sided test in this case as well. And once again, it's giving us very similar confidence intervals, 0.739 to 0.9901. And we get a more exact p-value. So remember, the exact binomial test is actually using the binomial distribution without using any normal approximation. And the prop.test is giving us the answers using the approximation. So they're slightly different, but they're really answering the same question. People used to tend to go to the normal approximation because it was so much easier to work with than the binomial test. Nowadays with computing, it just really doesn't make a huge difference as to how hard it is to use a binom.test versus a prop.test. Once again, we're only going to use the normal approximation if NP and NQ are greater than 5. If they're less than 5, then we should use the binom.test. But that's just a rule of thumb. So there's nothing to say that you couldn't just always use the binom.test. It might work slightly slower of a fraction of a second, but nowadays that just matters less and less and less. Just to show you, we could also change these alternatives. If we were doing a hypothesis test and we wanted to change the alternatives to greater, I believe that will change everything we need. If we do a greater than test, we should be able to get the p-values, right? And that's what we got earlier, the 0.04163. And if we do a greater than test here, we get our p-value of 0.0321. So we do get slightly different p-values. And once again, that's because we're doing an exact test versus a normal approximation. But just make sure your assumptions are holding true and that you're using the correct test based on your assumptions, okay? You can never go wrong by just doing the exact test versus doing the normal approximation, but you should only use the normal approximation when your NP and your NQ are at least 5. So I hope you learned something today about using R, and whether you choose to hand code things and make sure you get all the correct formulas or use the shortcuts, they're both equally useful, right? It's nice to be able to know that what a function is giving you is what you think it's giving you, but it's also nice just when you're in a hurry to not have to go look up the formula and just be able to use what's built into the system. So I hope you learned something today, and I will see you next time.